So Amazon just sent me an email saying, based on what you've been looking for, we thought you would like this. The 3 Wolves Howling at the Moon t-shirt. This is important. Asymmetric chain rings, which are they're shaped a bit like this. This is important. Cycling information, people. Cycling information. Asymmetric chain rings. 56, that's what I have. It's very delicious. Very delicious. So, it's just a nasty, it's not even like the Q rings, right? You know these things? Real cyclists don't even touch this stuff. Right there, oval shaped. Biopaste, well, so when you stomp down, there's more, and then less when it's coming over the top. Makes sense.
It matches to
where the power is, but so biologically, right? Like mechanically. But biopace was what Shimano had like 30 years ago, and they thought it was awesome, but it was 90 degrees off. So it was easiest pushing down and hardest. It's very strange. No one knew you'll see it. Danforth's bike has biopace on it. It's wrong. So awesome. Anyway, but it had that. It had banana cutters. It's pretty good. All right, so we're going to talk more about the small world theory thing while you eat candy, which really will put you to sleep, I guess. And it'll wake you up for a little while, and then that'll be it. Okay. What can I tell you? Has there been tweeting? There have been tweets. That's all right. Okay, so let's do this. Talks were great. Again, talks were great. That was a really great session. We also got through it, which was kind of spectacular. So well done on that. Asking no questions was important, because that, you're in an academic setting. It's like, oh, so you see this all the time, right? So there's the academics love to do this. I have 2 comments and a question. That kind of business. As soon as they say I have a comment, you're like, you obnoxious git. You are so full of yourself. Thank you for telling us that, but please have your comment. Just so obnoxious. And it's always about their work, how it relates to that. This reminds me extremely tangentially of my work, which is,
Invariably, they'll be the guy, say we had a conference and it was a 12-minute presentation, 3 minutes for questions, they'll be at the front of the line and 3 people behind them never did say anything.
Right. No, it's very, but give up. Yeah. No, people have different thresholds. We'll talk about this soon. Yes. All right, so small world networks. Okay, so we're moving from this thing to this. So we're going to think about why does this work, right? So why can people navigate collectively, distributed way around these social networks, around their social networks, to individuals who are a long, long way away from them that they would not be in contact with. All right, so we've talked about random networks. Random networks are cool, especially ones with arbitrary degree distributions. This is just a quick comment here. We won't calculate, but we know that, right, there's no clustering in random networks. So if you start at, large, infinite random networks, they're locally branching, right? They'll have some branching thing. So there's some average degree, and if you think about how that's going to play out, as you move away from this center node, you're going to get exponential growth in the number of nodes, right? They're 1 degree, 2 degree, 3 degree away from you. So you pretty quickly scoop through the whole network, right? You get exponential growth. Has to die away eventually, but you quickly get through it. And that flipped around means that the diameter or the distance, the overall diameter, and also the average shortest path between nodes in a random network is going to grow very slowly, like log n. So it's a good thing to calculate. You can assume a pure branching network, for example. And there are some fun ones to play around with analytically. There's the so-called beta lattice, which is just every node has the same degree, right? And so it's Hans Bethe, who lived to 150,000 years old and was still doing work at Cornell. Really did live for an enormous time. It's about nuclear chain reactions was what they were thinking about. Of course, some mathematician, for no apparent reason, did do this many, many years before, as sort of happens. So it's also Cayley trees. You'll talk about Cayley trees. But these are perfect structures, right? Okay. So you can think about, you could make one of those for yourselves and see how this works out. All right, so that's all a bit roundabout, but what I'm trying to say is that random networks have this geometric or topological aspect that we're interested in with these small world networks, these so-called small world networks, which is that, on average, nodes aren't too far away from each other. So it seems doable, right? It seems like you could get through it. Yeah. Okay, so population size, yeah. All right, so that's one aspect. But the problem is you can't, and of course social networks aren't random, right? You don't have this sort of structure. Your friends know each other. Very simple observation. So this isn't clearly the complete picture. It could be an aspect of it, but it's not enough. And so we'll see, theoretically, actually it works out pretty nicely. You can just sort of add randomness to structure and we'll get something. Okay, so we need clustering. Which is to say your friends know each other in some way. So here's a central node and they have connections. Their friends have connections, right? Very simple thing. And we've talked about clustering, how to measure it. There's the Watt-Strogatz one, which is what we'll talk about here because it's in this paper that has, 25,000 citations, right? Which is truly insane. Okay, it's truly insane. Oh, right, okay. I mean, if you get to 1,000 citations in 10 years, it's 100 citations a year on average. It's a lot of other papers which take a long time to write, and each other paper can only give you one citation. They can't cite you. They can mention you a lot, but it counts once, right? 25,000, that's a lot. All right, so we need something like this, and so here's a very, very simple observation. This is one of these things that should be kind of obvious once you see it, but it certainly wasn't beforehand. People were playing around, as we've talked about, with pure random networks, having a great time, Poisson degree distributions, let's count something else about them, they're fun, lots of analytic things. Again, none of them appear in the real world. So say A is trying to send a message to B, and it's this message game, right? So there's this probability of failure every time step. And A might sort of know something about the whole geography, they might know nothing about it. But we'll come back to that as part of this theoretical development. Right, they could know that they're sort of on this Manhattan weird Washington kind of grid thing and they know B is over there, but they can only move a message to their friend. And everyone's occupied, playing video games and stuff, right? So there's a chance that they will maybe doing work, but there's a chance that they will fail, right? So 10 steps is a long way. And there are, on average, kind of a lot of paths. This is a very structured landscape. And it's 2D. We'll look at the 1D version, which is the original thing. So if you add, and of course these are very specific kind of random ones, but the idea is you take a structured network, this is the big observation, take a structured network and add random links to it and you get what's become known as a small world network. We'll see that it fails in a very important way, but topologically or it's true. This is now the distance between A and B. A knows where their friend over here is, in this whole social landscape. So they know that they should send, of their 4 friends, 1, 2, 3, 4, they know they're trying to get to B, that this character over here is close to B. So they send that one, right? They have some map, which we have to get to. Like, how do they have this map in their head? So that shortens this world, and so all of these nodes here are now close to B, right? And if we think of this as airlines, then this is, right, similar to your project. That's collapsing this, it's changing this completely. If you think of diseases spreading on this, so instead of a disease spreading out from A, or a rumor or whatever it is, spreading out from A, from person to person, then it can jump, right? And this has become this huge problem. There are studies now, studies been around for a while, of if you think of people moving around on airline networks and you drop in Ebola or whatever and let it spread, it's very hard what do you do, right? Once you know it's spreading, do you just stop all flights? Well, that's an economic kind of disaster. What fraction could you reduce it by to make it okay? And you basically need to stop everything. It's pretty bad. I mean, we're very connected. We're super connected. So does that make sense? This is the basic story. And I'll show you the original paper and we'll play around with a little game version of it. But it's randomness plus regularity. They give you these two things. Regularity gives you some sort of social structure, right? There's some orderliness to it that makes sense to us as a local, right? We only exist in here. And then there's this randomness that helps us hop. So it changes a lot of things. In fact, I'm not sure if I mentioned it in here, but the original model, which is a total toy model. It's a toy model. It's not a real model of any social network. It's a toy model. It's a little game. People use that to sync supercomputers, right? So because there's a lot of local structures, just a few links on top of it can really change the way things work. So that's a bit funny. That's a socio-inspired algorithm. Yeah. And so that's interesting, socio-inspired algorithm. I believe JavaScript, the way it's built now, is inspired, or at least has been seen to be connected to organizational theory from the 1960s. Very strange. Okay, I gotta write that down. Yes?
You will tell us the paper.
Yes. Yeah. Well, I gave it in the big, networks are awesome thing. So we'll come back to it. So here it is. Next page. So it's 1998. It's an interesting thing. So collective dynamics of small world networks. Now, I'll give you a bit of history here because this is a big deal. So it's been found everywhere. In the original paper, they did C. elegans, which has about 300 neurons. Very well mapped out. We understand it. We know which things are connected to which. We actually have that network, right? This is, of course, a long time ago. You were small people, if you were alive. And getting this data was sort of a big deal. I mean, obviously, that took a lot of work by many people. So semantic networks of languages have this property, right? If you look at a thesaurus and then say, and we'll see how we have to measure this property, but they have this kind of local structure. They have clustering, right? Words that are adjacent to other words in meaning. Those words are also adjacent to each other, sensible. But then there are these kind of long hops. It doesn't take too long to search through the whole thing. Active collaboration graph, these two were actually in that paper. And the third one was, food webs are there. So people went berserk, right? So and this is before anyone cared about. So this is 2000. There are papers in PRE, Physical Review, about Marvel superhero comics because physicists, right? So they who appeared with whom, right? Important. I'm not sure. That must have been data lying around that someone could get to. This was IMDb, And this is a bit of a funny thing. It just means if you're in the same movie, then you're connected. So let's see. So as I said, this is two very weak requirements, that there has to be some structure in there and these random shortcuts. And that's in almost all networks that people have looked at of any large, decent kind of size. So it's a property that's found everywhere. We have to characterize how to measure it. Let me tell you a bit about it. So Duncan, so I worked with Duncan for 6 years at Columbia. But before that, he had a couple of postdocs. Before that, so he went to Cornell. Strogatz moved from MIT to Cornell in 94, right? Start of 94, right? So at the start of the 94-95 school year. So these two got together and they worked on a few things, and Strogatz is famous for synchronization, right? And all sorts of kinds of phenomena. The Firefly thing we heard about. But they started playing around with crickets, right? Crickets, because they synchronize, right? They get all this chirping, and they like to chirp with each other. So you get a lot of chirping, right? Chirp, chirp, yep. Cicadas are another good, very loud. I mean, above the threshold of pain, apparently, I think. Anyway, so, and I believe this is, as I recall, right? So Duncan was out in trees trying to find crickets, right? So he's climbing up, this is good physics, finding crickets, and they get them inside, and they'd have an electronic chirp, right? And they're trying to get the thing to chirp with this, and they're doing this over and over as experiments with crickets, right? So, and at some point, and that worked, right? I guess it worked, and there are lots of different oscillator stories, and you have to kind of take the cricket apart to figure out what's going on with it, I suppose, eventually. But at some point, one of them said, well, what happens if we had a bunch of crickets, right? We know that if we have a whole bunch in a tree, they all start chirping together, right? But what if they could only, so you've got your cricket here, and it has a set of headphones on, and it can only hear this cricket and this cricket. What happens then, right? And then you put them on a network. What happens if you put your crickets on a network, right? So they've got little tubes, and they can hear each other, and that's it, right? So they're not listening to this one anymore, and this, right? So what would it synchronize? Would it work? So that was the question they started off with. Yeah. So what happened? Well, that would be great, but headphones is typical, right? So computer simulations, yeah. So the crickets get left in the trees, and then we go and make models on. That's what Duncan did. Spent a lot of time coding things up, and there are various kinds of models that they came up with. But we'll see what the original was in a minute. But that was the inspiration. And they didn't know about the Milgram thing at all, right? So this was presented at Rockefeller, like this kind of thing, and with this synchronization story, and who was it? I've forgotten. A famous guy. Anyway, mentioned, oh, this sounds like the small worlds thing, right? So they get the small worlds story in there, and they put in the title. They sent it to Nature, and they had 2 reviews, which is not atypical, but one said, this is just percolation, we've done it all, which is great. I mean, it's so ridiculous what happens in peer review, but, you know, and we know this with Harry Potter and all these sorts of things, right? They have these enormous successes that seemingly a number of people just said, that's no good, right? I think Harry Potter's 13 publishing houses. I mean, it is a giant phenomenon, right? It really is, of the modern era in terms of books. But 13 publishing houses said, like, no, no. And the last one was because the person is Bloomsbury. Is that what it is? The English. I've got that wrong. The granddaughter, apparently, of the CEO said, I kind of like this book. So anyway, but all these people were sure it was it's not going to work, right? So. And we'll get to that later on, because that is a big, big deal about fame, right? Why do things take off? But the other review was, this is great, I love this, this is really good. So they have to go to a third person, who we know who it is, was basically just said, this is awesome, and it breaks the tie and gets published and just explodes, right? But it had this dangerous thing. I mean, it would have been published somewhere else, but Nature's a pretty good, if you get that thing. Although, of course, so many horrible things get published in Science and Nature. But it does help it. It always helps it. It puts it in front. Okay. So it exploded, and a little bit of fortune at the start. Duncan turned his thesis into a book, and that took off as well. So let's see if we can do this. So this is the paper redone as an app. And I've said this for a long time, right? Papers should be apps, and a lot of papers should be apps, but PDFs are kind of horrible, I suppose, much as I spend my life making them. But this is a little website. Let me get it to work. So you can read through this. I'll link to it later on, because it's you should read the original paper's 3 pages long. But here's the idea. It's got a few little pieces, right? So it explains. So let me see if I can explain this using this thing. Okay, good. Right, it's simply laid out. It's got the same title. It's essentially redoing this paper as a little web page with some happy bits. So you've got something, 12 vertices, and then you specify some number of vertices. This is the general model. And then for each node, so it's very stylized, each node has connections to some number of friends on either side, and we use the total, right? It's their degree. So k equals 4 means that everyone has the 2 next to them, and then the 2 next to them, right, are connected to them. So you're on a ring. So the layout is important. You're on a ring, so you're connected with the people next to you, right? And if k equals 2, you'd just be that, just a ring, right? It'd be just a little ring. So this has kind of got some, and so here we're sort of showing in gray the rest of them. Does this make sense? Sorry, make this bigger. Make this bigger. Oh, look at that. Enhance. Okay. All right. So here's the algorithm. We're going to do the whole thing. It's great. Okay. So this is how we start with this, and then there's a little get. So this is a regular network. This is a regular structure, right? This is this regular structure we talked about before. So again, this is a bit of a funny thing. You can change this, and people did evolve it a little bit. But here's the original model. You go around and to every edge, so you go around each node like this, and every edge that's pointing around in this direction, you don't take its edges going back this way. So each one of them there are 2 links. Pick up the other end with probably P, you pick up the other end and randomly rewire it. So there's a P. So if P equals 0, no rewiring, right? If P equals 1, every edge is rewired. So let's say that one is successfully chosen. So you roll a little thing, right? And it turns up, say rewire, right? So P might be 0.05, yeah? It's a 1 in 20 chance. You roll a 20 on your 20-sided die, which you just have, right? And you rewire it, not a random rewire where you pick it up and put the whole thing somewhere else, right? It's always going to be stuck to the original one. And then you rewire the other end randomly. It could go back to where it was, but and not to itself, right? This can lead to the network falling apart, and I think in the original model they just discarded those. But generally speaking, if you've started off with enough extra friends here and you rewire, it's going to stay together. So just keep going all the way around. Well, there's a little slider. Let me see if that works. This is great. Yeah. Right, so these are being rewired, not all of them. So some of them are staying intact, like that one stays intact. Does that make sense? Didn't move. This one, the next one gets rewired. That one stayed intact. That one's rewired, right? Boom, 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 boom. Okay, so it's been rewired to some extent. And then, so this is what I said before, p equals 0, you'd stay where you were. No one's rewired. This is some degree of rewiring. If p equals 1, you get it's not quite a random network because you aren't just picking the nodes up and the edges up and putting them, rewiring both ends. The way this is done means that at least in this, right, this is something where they have 4 friends, they have 2 friends going in the clockwise direction. They will always have those links. They don't get broken, right? They just get rewired at this end. If they do, these ones can be broken off them and they can have new ones added. So everyone has at least 2 friends in the end. So that was a sort of a way of trying to preserve the thing from breaking up. So this is a way of traveling from one kind of network here to one kind of network here through network space. Network space is gigantic, right? It's a gigantic thing. Here's a reasonable way to sort of, or a useful way as it turns out. So this is dialing from p equals 0, right? Increasingly more and more messed up to random. So we can test this sort of thing, this small worldness, right? So this isn't a small world thing because it's got clustering. Some of your friends know each other. Not all of your friends know each other, but some of your friends know each other. So it's got a clustering, which is not what random networks have. Very large random networks have 0 clustering, so it's different to random. But it takes a while to get messages around here. Yeah. This one, no clustering, so this has lost its socialness. Yeah. But on the average path length is small. So this has one aspect of the small world property that we want, right? Clustering. This has the other, and then the idea is, well, what's in the middle? So you want to see that clustering holds on for a while, if it does, and then the average path length goes down. And so that's the game. What else have we got? Yeah. So this is the average shortest path, right? Boop, boop, boop. So this is finding the shortest paths, for example, between every pair, which we've talked about. So this is you go and find the shortest path between these guys, right? So it's 2 steps. Okay, very good. And then this is clustering. The same story as before. It's the Watt-Strogatz clustering, which means you look at this one has 4 friends in the resulting network, and you look to see how many of them are connected. That's what all of this is, right? So these are the connections between this node's friends, and then you average over all of that. Actually, I got that wrong. These are all the possible friendships. These are the ones that actually exist. Excuse me. Right. So the clustering for that guy is 1, 2, 3, 4 divided by 4 choose 2. That's the fraction of its friends that are fraction of the possible friend pairs that exist. Yeah. And again, in a random network, it would be 0. In a very highly clustered network, it gets closer to 1. But moving away from 0 is a big deal. Okay, so we're going to measure those 2 things and this. And so you measure them all the way through, right? So you vary p from 0 to 1 and measure those 2 quantities. C for clustering, L for average path length. And then this is any more little slidey things? No more slidey things. Okay. Yep. And then you can look at how this thing grows with the number of nodes, and that's what's being played around with here a little bit. Okay, all right, so let's let this ring grow and grow and grow. Good, very important thing to do. We're going to let it grow. So the average path length grows like n over 2k. It just gets linearly bigger because this is ring, right? There are no shortcuts in there. This is a thing to compute. The clustering is actually 3/4, which is pretty high. That's a very high value. You can compute that for the original one. Depends on k. for the purely random or the randomized version, as n increases, we get bigger and bigger rings, the clustering decays. It's going to go to 0, which is the story we've had before. And path length grows slowly. This is this logarithmic thing. So we want that and we want that. Right. And this is the story, right? So I wonder if there's an n being displayed here. It's a pretty large network, presumably. 1,000 vertices. There you go. 1,000 vertices. Everyone has 10 friends, 5 on each side. It's a tiny network. Is that what you're saying?
No. It's just that the clustering very, very small.
Right. So this is logarithmic, which is an interesting point. But basically, what happens is as you start to randomly rewire just a little bit, that's really the upshot here, because this is a logarithmic thing. This is 0.0001. 0.001, right? These are small. Everyone has 10 edges. Yeah, right, the average degree is 10. Right, it's built in. All right. Yes. Yeah, so you have 10,000 edges. The way this thing works, there are 10,000 chances to rewire an edge. So this is 10 to the minus 4. So this is rewiring just 1, typically. Right, this is rewiring 10 out of 10,000, just 10 of them. So 10 of them means that the clustering, you've only rewired 10, so you really haven't broken up the underlying structure, right, out of 10,000. Yeah. So it's still high level of clustering, but the path length is really, the average path length has really decayed. So you've got this, you've got some giant ring like this. I mean, it gets bigger and bigger, and you just add a few things like this, and it really starts to cut down the average path length. And so that keeps going. Clustering eventually has to decay, right? As you randomly rewire this thing, more and more severely it has to decay. But the path length's getting better. So there's a sweet spot in here, as indicated by the spoon, right? Where these are, we'll sort of think about these things as being small world networks. And then real networks often are in this box. They have high clustering, low path length.
So this is really neat. In economic history, a lot of things you'll study is exactly the scenario. So say you have all of these different connections, and say,
Yep.
They're early 1,000 to 1,100 or something. You have all of these very, very, very strongly clustered. People are in their home villages and cities and such. And you just get these very few big trade routes,
Yeah, it changes everything.
But as soon as these things start getting established, as soon as these shipping routes from, the one shipping route from Britain to India at first, everything just begins to, the world begins to...
It changes enormously. It changes enormously, yeah. And some of those things are diseases, right? I mean, there's some bad things happen, right? But yeah, you unlock tremendous change. So I have, I guess she was a PhD student, Emily Erickson, who's at Yale now. She was at Columbia when I was there. Did a lot of work on that, the trade route stuff, right? So you can see all sorts of because they're network stories, right? You can see where the Dutch were going, where the English were going, where the captains were also going when they said they weren't going, because they have all their logs. They're good at recording. They're good at recording the bad things they did to other people and all the money they made, right? But they also do all these sneaky little things where they would go off, didn't tell anyone, a little bit, because you'd move some stuff from here to here and then come back to England or whatever, right? Anyway, so there's been some, just to expand on that, a lot of good stuff there. Yeah, big changes as soon as you add. So I sort of said this before, but I was going to say this before, I guess. So you can see how diseases spread, there were trade routes, so that sped things up, but medieval times and before, it's more like a wave across the landscape, right? You can see, because people, of course, kept records of there's a documentary of Bringing Out Your Dead, right? So that you see the records, again, a documentary. You can see how it spread across, and people have done a good job of doing that. But that's not happening anymore at all, right? Because now we have, especially with that trains, planes, and automobile thing, you get this, boom, someone's sick from Hong Kong, suddenly Toronto is in trouble.
So without planes, trains, and automobiles, can you model disease spread by a wave phenomena? Can you solve a wave equation or something like that?
I mean, it basically looked like a wave front, and I don't know if they solved it, went as far as doing that, but it would just work because you'd have people's sort of ability to move, right, would be in there. That would be the wavefront. Yeah. But it is more like just a spreading thing, and of course just leaving a trail of
random distribution of people, particles in the landscape.
Yep. Yeah, so it would be more like a so I know I've said this, right? Ripples. So you drop a stone into water and you get ripples, so that the front of the wave is going out in a it's a circle growing out from the center, but there's structure all the way out from the original one, which doesn't happen in 3D or odd dimensions. Odd dimensions, it goes out as a shell. And so that's why when we talk and listen to it, it just goes straight past, which is good. Like you hear it and it's gone. Otherwise it'd be like a piano with a thing held down, right? It would be coming the whole time. But that's not, but in some ways the disease thing is not like, it's really just a ring going, yeah. But you do have, this is true, you do have resurgence, right? We'll talk about this with disease spreading. The simple models, they all go like this, people get sick, they get better, right? Or they die, or whatever it is. But in reality, it's often like this, is resurgence, which is very problematic. And there are reasons for that, that we can get to in a simple way. But it is to do with somewhat rare movements of people, which is kind of what you're saying. We're actually going to, we're going to run a one-day conference next. We've done these TEDx type things over the years. We've had big data, big stories, big scale, big fail, question mark, ellipsis, question mark. And then we had big predict, right? Oh, no, just predict the next big thing. We're going to have one on pandemics. I want to call it big spread, big dead, but I don't think I don't think we can do that because it's totally right. Anyway, pandemics, as we'll get to, horrible problem because no one knows how big they'll be. Journalists will call up or whatever, or the government. Like, how big is this thing going to be? No one has any idea usually. They really don't know, right? That's a hard thing to predict. Anyway. So does this sort of make sense? It's a toy model. These things don't necessarily exist, but their flavor exists in the world, right? There aren't these little funny, this isn't a social network. Fine. But it just, this, and it will seem sort of such a simple thing now, but this was, this just opened up this massive kind of block we had about graphs and networks and reality. And that's one aspect. It's just one feature of what turned out, we're always looking for universal stories or things that are true about a lot of networks, and this really got people excited. Okay, so that's good. I think I've played with all the little thingamajigs, but you can read through it because it's the original paper is very short. You should read the original paper, but this is also just really nicely laid out, and that's it. That's your paper, right? Yep. This was just a plan to make it awesome, comic style. Yeah, it's great. Okay. Love it. All right, we'll go back to building PDFs. Okay, so it's cool. Yep. Okay, so that's our thing. We understand it now, I think. Yes? Yes? Pretty cool. And that's it. You become a very famous person if you think of this little story. Yeah, okay. So, here's the problem though, right? So this is awesome. People do the comic book thing. They go bananas. They find it in social networks of dolphins because you can. So this is an unfortunate problem. So it turns out you cannot find, this is just the structure we're talking about. Short paths, clustering, these are just structural things. If you let a little algorithm loose on this thing, and these are big enough networks, can you get from A to B, right? So we need that they're short, we needed this thing that they're short. The paths are on average short, that's important for getting the message through. We needed the clustering thing to just even give it a sense of socialness. That has to be there, right? Just the minimum things. But it turns out they're not findable with any, so the algorithm has to be, you can't have an algorithm that knows everything, right? And that's not good. Mazes, that's not the plan, right? Here is a crazy maze and then someone says, oh, my algorithm works, it knows exactly, that's not what we're doing. So they don't have a map, it's a distributed thing where the message comes to a person, they're like, oh, a message, and then they have to hand it to someone else. And then that has to happen again and again, and it's distributed. Right? No one has a big bird's eye view. So this paper, So we need a more sophisticated model. I'll show you a couple of things that people have done. I missed my thing. Whoop. I want to click on this. So this is John Kleinberg. Navigation of Small World. It's a one-page piece. And I'll probably talk about it again, but I might as well just bring it up. So it's a one-page piece. So it's navigation, right? So this fixed everyone's brain up. This is 2000. Yeah, it's 2000. Introduces the algorithmic side to search. I mean, it's about search, right? So it's not just the topology or the structure of the thing. It's about the algorithm you put on top. So Kleinberg, who I've mentioned, very smart person, lovely guy. He is at Cornell, and he has a MacArthur genius character, right? Rightly so. So he said, all right, there's this. The network thing is cool. Let me think of a very kind of different, not particularly social, but it's a sort of a network. So it's going to be a d-dimensional lattice, right? So this is something he solved for d dimensions. So it's a lattice, but it's got finite ends, right? It's a little box, and the same idea as I kind of showed you in that grid, the lattice at the start. Someone is trying to get from somewhere to somewhere. I guess U to V. And his general, and we won't go through all this. It's a lot to figure out. But his story is okay. So we're going to do something a bit like that original model. Set up the lattice, then put a diameter, a little sort of ball around each one, and connect everyone who's in that ball, right? So you kind of make a radius. So you get the clustering thing locally, right? So same idea. Makes a little ball, and then add random links. But different to the Watt-Strogatz thing, the links are added with some probability distribution. I know I have this in the slides. I can't help myself. That decays, right? So at some point you're adding random links. If you dial a parameter, you're adding completely random links, or you could be just adding links that reinforce your local structure. So he has a thing of tuning the network in a different direction, and then also allowed for any algorithm, so computer scientists, I suppose, so any algorithm that used local information. And I'll show you what he got to there. Okay, so let's go back to the thing. Okay, so it has to be a local search, because we're trying to at least recapture what people have done. Yes, you can do more sophisticated things. Maybe this is not of value, but we want to sort of understand this Milgram thing. So you haven't got a map, right? You just know about your friends. You know about the target. You may be given a lot of information about the target, right? But you know the game is, how to just go to Google and find them. That's bad. So you know something about their identity, of course. You know something about your friends. You know their identities, their popularity. Like your friend here might have 1 billion friends and so on. Or you know something about their reliability, all these things. And you know where the message has been. But this is now bringing it down to kind of an algorithmic thing. Popularity is just how many friends they have, their degree, right? Identity, this is a piece we'll get to. And you know where the message, so this stops people from, at least or in this algorithm, from just sending it back to where it was, where it's been before. So it stops loops from happening. So you can imagine the message comes to you and it's been recorded where it's been. So that's sensible. History could be on it. Yeah? Yeah. Okay. So this is a game. So this is Kleinberg. He allowed these two things to vary, which I've tried to point to. So a local search algorithm that could use only those things, any arbitrary local search algorithm, and the network structure. So now he's allowing these things to play with, and this really wasn't in the Watt-Strogatz thing. We said, we found small world networks. Kind of, right? They were not searchable, actually. They were fundamentally not searchable. So, you make them bigger and bigger and bigger, then the scaling of search time goes up and up and up. So this is a different kind of game. And so d-dimensional cubic lattice, going to add links, reinforce local links, or create this local structure by just adding links to nodes that are within some distance. And you can tune that. And then each node gets a bunch of shortcuts. M equals 1. Just add one shortcut for each node. So it's going to be from them to somewhere else in the world. And this is the plan. So you can play around with this, and we'll do it in different ways. The probability that I connects to J is going to be proportional to the distance between them, and this is just a lattice distance now. You can make it a Manhattan distance, or you can make it just a Euclidean distance. decaying with some power. And so this is a tunable object here, right? This alpha thing. Yep. All right, so alpha is 0, then this is just a constant, right? So it doesn't matter what it's connecting to. Every other node is equally likely. So that's a random, they're making random connections. So that puts us back in that what Strogatz kind of thing. If it's large, then it's decaying really, right? So you want to reconnect, you want to connect to nodes that are around you, reinforce. You should pass that bowl around some more, please. This is a mercy gesture, sorry. I think you should be able to just yell out candy if you want. Throw some tables over. So that's what my children do. No, they don't. Okay, so he did these things. And then if alpha is d, that's an interesting thing, right? Because now we're talking about d dimensions, which is a bit funny, but we're talking about d dimensions. If alpha is equal to d, then that means you're adding links. You have to think about this a little bit. Connections are growing logarithmically in space, right? So now, I've drawn this a bit funny, but imagine this is log of r, right? So these shells are growing around this initial node, and it has an equal chance of sending connections out into all of these areas, right? So alpha is large, it wants to just connect to its neighbors, really reinforce it. Alpha is 0, it just connects randomly. But alpha equals d is quite special. It means that you're kind of going out at all scales. Right. And it turns out that is the special, for these networks that he's making, that's the special network. That's the most searchable network. And the best algorithm is a greedy algorithm, which is simply that you send candies on the floor, people. Okay, so greedy algorithm, which is that you do the simplest thing, right? You're a node, you know where the target is, you do have a map here, right? That's very important. You know what your location is in this big hypercube thing, and you know what the location of the target is. So by identity, right, it means that the person you're trying to get it to is here, and they have coordinates, ij. You know those coordinates. You know your coordinates. So in principle, you could just go bonk, 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 right? You could do that. But if you have friends over here, that's going to help. So and you know exactly how far they are away. Because in your head, you can say, here's the distance between them, right? There is a map. Okay, so everyone's sitting actually in space somewhere. If you have random, so here are the two extremes, right? If you just have local connections, then you're kind of forced to do this, just to kind of push the thing along. If you have these long random connections, there's just a chance now and then that you'll get a free ride. But they're a mess. And the random connections also, if you say get out to here, all these connections are random, that's not going to help you with this last bit. So it's a lot like, and this is a horrible game, I speak from experience. I was playing this as a kid, I stopped playing it. Golf, right? This is like golf, right? So this means you've got a bunch of woods, and you just smash the thing, and then you have to just sort of like kick it along with a putter. This is putting the whole way. This is having just a wood and a putter. And this one means you've got the whole set of despicable game, just an awful game. But analogous, actually. So it's a social golf. It's a social golf. So you need the full complement of objects in here, your irons, your wedges, the sand wedge, to help you get all the way there, right? Does that make sense? I could try for another analogy, but unfortunately I think golf is the right one. Flog, spelt backwards. I mean, come on, it's the Scots. I mean, what are they? It's designed to make you suffer. Like Boston's traffic layout, yeah.
Yes?
Yeah, no, it's the Puritans just built it into the infrastructure. Very clever, yeah. Yeah.
So I have a kind of an in-depth question. Is that so?
We'll see.
All right. So,
I'll put a big one for you. Okay, all right.
So
Is that bad?
we're talking about local regularity, and this depends on local regularity. Now, local implies use of a measure, and that's fine. We're using a measure in
Correct.
this graph space, and this measure we're using say is the k, so we're saying,
Here it's very simple. It's just a lattice. There's no funny business.
So that's fine, but regularity means, of course, probabilistic regularity, because
Yeah.
right, obviously not every local,
Yeah.
prime by d prime little cube.
It's a very contrived thing, but that's okay.
So-
But
so-
it's analytically tracked. So that's what it is. Toy model's good.
So I'm just curious. So this is a probabilistic regularity, which means that we're saying on the grand scheme of things, almost all the time we're going to have this regular structure, although sometimes, of course, we will not. This means there's a probability distribution of the length of the path of getting to another node,
Mhm.
because most of the time you'll be able to find via this greedy algorithm when the path length is when the exponent is alpha equal to d. Most of the time we will be able to find this.
And in fact, yeah, the search on average will grow like this. This is a result from him. So
Yeah.
let's have a log squared n, because that's awesome.
Pseudo-optimal algorithm. It won't actually be optimal probably, but it will be close.
Oh, well, that's true, but it's great because it's a pragmatic little beast. Although, he proved this. It's kind of nuts.
So
Yeah.
we'll figure out the probability distribution, because then sometimes it'll be truly terrible. Just absolutely truly terrible.
Can it be awful?
These tail risks, because of course it can be awful.
That's a good. Because of the way this is constructed, it's in a hypercube. There's an upper limit because you can always just
Yeah, of course you can brute force.
say I have no idea. The best thing I can do is just move it one. So there's an upper limit.
With an actual max cutoff, but
It's n to the 1 over d, right?
yeah.
You've got n distributed through a d-dimensional box, so n to the 1 over d is a typical length.
Yeah.
That's the smallest time. That's the longest time scale. So it's constrained. It's not going to get out of control. So because there's a map. There are
Yeah.
positions. You know where you're going. Some of the others you give up because you can't. There isn't a map. You don't know which friend to send it to. That's when it's bad, right? So that's when it's bad. But that's more realistic, and we will talk about it. Yes, because this is true, right? But certainly this is not so, right? So we've moved a little bit closer to something that's, we've introduced search in a proper way, just was absent in the original model. It's an expansion, and we're playing with the network and the search algorithm at the same time, dialing those things in different ways, and finding this it's kind of a very nice result. Otherwise, away from that rather perfect structure of network, the best search algorithm scales polynomially, right? So it departs from it, yeah. I mean, it's not bad, but it just starts to move away. And in fact, it's on this. This is the exponent in the search time, right? So this means it's a log, basically, it's a log. And here it's polynomial, and of course he found the results. But it's polynomial, I think. Yeah, right. So, yeah, but let's do this. Okay, it's a fun model to play around with. People have worked on it. There is a Vagro, I think, is in this list here. So people have done all sorts of things. So if you want, you can get really excited. Of course, people put on a Sierpinski sieve because why not? That's awesome. So, physrevlet, a couple of those, right? So that's just to show you that goes off. So Lighter-Adamic, this is 2001. I always thought it was Adamic, but it's Adamic. 2001 showed that if you have these scale-free degree distributions, those kinds of networks, then you basically get to a hub, right? So you go and find your friend that has the most friends. You send the message up to them, and they keep doing it. Then it's somewhat more searchable. When you get to the hub, that person has to be able to go out from it, right? They have to be able to know which way to go. That's a bit shaky. I mean, if it's a few levels away from them, then that's a bit harder. But that helps. And of course, humans are, if they're real humans in here, then no one has a billion friends, right? There's the the Dunbar story of 150, as many as we can kind of handle. And if you think about how many people you can email with extensively or send text messages to or actually talk on phone, that's a old technology. But then, it's pretty limited. It's pretty limited, right? Of course, people have millions of followers on Twitter, but it's a different thing. So, good luck getting Bieber to retweet can you find this person for me, please? It's not going to happen. Okay, so but that was a different thing. I'm going to say this is really true. This is around the time where everyone thought everything has a hub in it. All networks are scale-free networks, because that would be great. Not true, but we'll talk about that next. Okay, so I'll tell you about, this is work that I did with Duncan and Mark Newman, right? So if we don't have this, so Kleinberg has moved the story along very, very well by getting us to think about algorithms, right? But we're still stuck, the structure, that network structure is still not a social one, so it doesn't apply very well. So, if we've got some sort of weird looking network like this, how does A know how to get to B? How do, they know they've got all these friends over here as well. How do they know to sort of pull out the golf club that they need, right? So you need some measure of distance. We'll come up with a funny one that probably, of course people would have heart attacks if they care about measure theory, but it's a measure of distance of sorts. So you need to figure out which of your friends is closest to the target person and then move it to them. All right, so let's put in identity, which is really what was underlying the Kleinberg one, and of course, actually there was no search in the original one, but not talked about so much, but so you know where they might be. Of course, this is going back to the Milgram experiment. You know what they might do, all various things, right? You might know something about them. And this is so this is more generally just talking about identity, right? Your identity, you can go and get all crazy about it, but basically it's the sum of the things, if you like, that you do, that you're interacting. And that brings you into contact with other people, and that's a way that social networks can evolve, right? You get into classes, and you can meet people because of that. Very natural thing. So we'll say then groups are formed if people have a similar attribute, right? They may be stuck in a class together, but maybe they like playing a particular sport, and so they join a team and they become, right, whatever it is. So you have these attributes that bring you into context, that give you interactions, and then the network lifts out of that, right? So this is I'll have it again, but this bipart affiliation thing, boards of directors, interactions between them, they become connected, and then the boards become connected in interesting, opaque ways. But this is why social search can work, where you're trying to get to a lawyer and you play basketball with someone who's a lawyer and they know them, right? But the distance between you and that lawyer is very large. So the triangle inequality is going to explode here, right? So we'll do that. Okay, wow, this is a brutal use of colors. Okay, so using XVig, yes. All right, so not ashamed. So let's see, so you've got these contexts that people are involved in, and this might be just where they live, or the classes they're in, or whatever it is. And right, so here are the individuals, A, B, C. So B is sharing these three contexts with others, so that's how B knows A, and that's this connection, right? So you get this projection from a bipartite affiliation network to a unipartite one. And we tend to kind of want to build here, we want to make a network of whatever it is, dolphins sort of out of some mechanism and build it here. But really a lot of things operate in this way, and you need to be building this structure. And this just been amazing, beautiful work early on by especially Newman on bipartite networks, random networks. Okay, so this example, E starts going to tango lessons or whatever it is over here in 3, and then that brings them into contact with people that they weren't connected with, right? So they're already connected with C here, but they were not connected with D or B. So now they're going to get those ones, right? So E has got B and D as potential new friends. And you can make it probabilistic, right? If you're in a context, there's a chance that you get to know each other. You can make it absolutely 100%. So this is movies and actors, right? Boards, directors, etc. And you can see how this starts to evolve then. And then, you're introduced to maybe new context, but you're probably more likely on a smaller time scale introduced to people in your contexts that you work in already, right? And then maybe you expand your context, right? You become a huge fan of solving Rubik's Cubes in a speed, whatever it is. So you join that group, that becomes a thing for you. And that opens up a new social aspect to your social identity and gives you new ways to connect. So This is a potent thing. We call it the generalized affiliation model. Let's run out of space there. But here's how we get distance into this, right? So let's leave the individuals by themselves to start with, so to speak, and then we'll have some sort of structure imposed on the affiliations, right? So maybe this is the occupation thing. So people have occupations, and you could include here, no job. That's sort of in that category, right? This is a very simplified story. So these people are teachers, right? Not in the same place, but they're teachers. So if you go up a category, they're closer to each other than they are to these characters, right? So you can start to build a hierarchy, and it depends on the aspect of identity. This might make sense for occupation, things that categorize like this. We'll do a crude thing where we just take all of them to be hierarchical, but geography would be something else, but it's not just 2 dimensions, which is messy. Depends on where you've lived as well, so you kind of have those strange connections. Age, right? That's another thing. Okay, so let's do some, try to actually get a measure out from this. So, all right, so we've got these 3, we've got new here, and then these 3 other characters, I, K, and J. Right? So there's some hierarchy, and we'll structure this as saying there's a group, there are these groups, right? So this is your basketball team or whatever it is, yeah? And these are the people you play or you see who are sort of most similar to you, but they're in a different group. So the distance between, let's say I and K over here would be, we'll define it to be 1. If you're in the same group, it's 1. If you're in the same, and then it's the lowest common ancestor, right? So the distance between I, K, and J over here is going to be 1, 2, 3. That should be what this is, 3, right? And then I and V, I guess it is actually 4, right? Because there's a 1 just for your group, 2, 3, 4, and then it descends back here. So that's a very sort of rough thing to do. Okay, yeah? So you need some categorization of identity on top. And then, so of course if you're closer to each other in a hierarchy, you've got a better chance of connecting. This is then something like, not quite the same, but it's something like the Kleinberg story, right? So the probability of 2 nodes being connected is proportional to the lowest common ancestor distance. It's got an exponential decay, which sort of makes up for this logarithmic thing with hierarchies. And again, we get these sort of 2 endpoints, right? If alpha is 0, there's an alpha in here. If alpha is 0, this is just a constant, so it doesn't matter where they are, right? The hierarchy doesn't exist to you. Then you're making random connections, right? You're just randomly linking. And alpha is large, you get local connections, right? So you're preferring to connect to individuals who are next to you. So you can play around with this. Again, it's a toy model, but it's sort of a lifting into a more social kind of thing. How do we feel about this madness? Use this again, it's good. But then we also, of course, have more than one identity, right? So geography, occupation, age. Now age, fair enough, right? It's probably on a linear thing, but you could bracket this. There'd be more structure here, middle age, whatever it is, right? So there are more reasons to be connected to people of a similar age, and then all sorts of other complications, I suppose. But basically, yeah, there's a plan. Where you live geographically, geographically, maybe that's, I don't know, how do you represent geography, right? So we don't, that's a craziness. It could be just a map. So now we have, node A and B. This is similar to this bipartite story in general. Right, they're close to each other. Let's see, A and C are close to each other here in geography, but not in anything else necessarily, et cetera, right? So if you start adding these links to each other in these by their hierarchical distance, then you reinforce this structure, you reinforce this structure in a natural way, right? People aren't connected to each other if they're a long way away in geography, et cetera, right? And there's a great history of sociology for this. Google Plus, this thing that's wilderness, just sitting there on the web, they really tried to build that in with circles, the circle structures. You could build these little circles, which what people do. I don't know. Well, if it had come first, maybe it would have been great, but it didn't. So they're trying to really build in a social thing. Okay, a couple more pieces. So now let's say you've got 3 hierarchies. We've got I's identity is here. here and here, whatever they are, you know, so again, it could be geography and occupation and maybe some recreational activity. So they're very separated, right? So the distance is whatever it is, 1, 2, 3, 4 here. Here it's 3, they're a bit closer, but they're still far apart. But in this one, you know, they play on the same team, right? So this is how they get to meet each other. And so we can write down a little identity vector for all of them. So 1, 1, 1, we're just going to put the position that they are, the group they're in. So it's 1, 2, 3, 4, 5, 6, 7, 8. So I is in 1, 1, and 1. And then J is in 8. That's 4 and 1. And then you simply take the shortest distance between them. So this is the distance in the hierarchy. So they're 4 apart in the first one, 3 apart, if you like, the distance, and then 1 in this last one. And then we just take the very simple thing, we just take the minimum of all of those distances. You know, again, still very much a toy model, but we're trying to impose some more social structure. Okay, is that sort of okay? So you take the minimum over, you take every pair of nodes, you construct all these hierarchical categorizations, and then we take the minimum over all the hierarchies to get a social distance out. So there's no underlying grid, right? There are these underlying hierarchies, but they're based more on identity. So the triangle inequality, as I mentioned, is not part of this game. So I is a long way away from J and K in this story, but close to J here, and then far away from K again, right? So this is, you play basketball. Sorry, they play basketball together here. These two are lawyers, right? So I is trying to connect to K. It links to J here, and then J over in this hierarchy, J links to K. So the distance between I and K is 4. It's always 4, right? They're always as far apart as they can be in these hierarchies, which is greater than the distance between I to J and then J to K. 1 plus 1 is 2. Yeah? So that was something that was observed, actually, mentioned in the sociological literature on social networks. So just the example I give you, right? It's clearly not working in a way like a normal metric space, right? I say these words. Okay? So it captures that, which is a nice thing. All right, so let's do a little game with it. Again, people know themselves, they know their friends, they know their target. Now we're talking about these vectors of identity, and they can simply estimate the distance between them, their friends and the target by just looking at the two vectors. And we'll just use a greedy algorithm and then have a random search failure thing. Right? We'll just sort of put that in as well because that happens in the real world. Let's interpret this. So this is many hierarchies here, right? So this is 15 hierarchies. So it gets a little messy as you add too many ways to search, right? If you have too many parts of your identity and they're all equal, that actually makes it harder to search. But so it's good to have maybe 3 that are dominant that you navigate through, and that comports with the experiment, right, which showed that it was more geography and jobs that got people helped people navigate through their social networks. So you do very well, actually, for this is the alpha equals 0 case. You do very well with one hierarchy, actually, right? So one hierarchy is fine because when you've just got one hierarchy and you've got random edges, that's going to help you navigate around that thing pretty well. But when you get to 2, those random edges tend to overshoot all sorts of things, and you're much better in the case where you are right? So your net is your hierarchy, a couple of hierarchies. When you're adding links more locally, which is much more of a social story, right? That's a natural thing. So alpha equals 2, I know I'm just showing all these things. Alpha equals 2 was that exponential decay. So that's fairly strong. Yeah. So too many dimensions, it kind of goes to bits. Yeah. Yep. Maybe I've said the wrong things. No, that's right. So this is the chance of getting through, right? This is good. There's a good searchability here. This is a 0.05 we're just using here as a 500ths. So this one, of course, this one is when you've ramified locally and you've only got one hierarchy. That's no good, right? Because it means you have to go up and down all the time. That's bad. It's just one hierarchy. As soon as you add another hierarchy, and here's the tricky bit in this. The hierarchies, they're randomly shuffled between hierarchies. So that's maybe too much, right? So we've randomly shuffled their identities. That allows for these kind of random connections to come in. And then we tried to do the Milgram thing, right? This is actually from Milgram's thing. These are the Nebraska to Boston chains. There are about 200 of those, and that's this. There are a few that got through. They're only of length 2 if you send them from Boston. So we used estimates of things from the late 60s, so about 100 million people in the US. These are, again, taken from the social literature, about 300 people. For friends, groups, typically of 100. These are just all rough things. Branching ratio didn't matter too much. We've got to put a branching ratio in these hierarchies. That doesn't matter too much. 2 hierarchies and alpha equals 1. So that's sort of 2 main things that people are searching through. So it's not cherry picking too much. I mean, you see those numbers aren't like absurdly tuned things. They're sort of, they're tied to the reality of that time. We got these things to match up pretty well. Which seems incredible, I have to say. But yeah, right. So that was incredible. All right, so that was pretty good. People have gone. So again, this is Lada Adamic, who's in charge of a Facebook data science team. Now, she used to be at Michigan, but she moved over to Facebook. Before that, she was at HP Labs. So they looked at whether these kinds of connections make sense. So they looked at how likely people would be connected as a function of where they actually sat physically. And that seemed to decay like a 1/r thing. But that's the exponential for, so the exponential that we just made up worked pretty well for organizational distance, which was kind of what we were going for. So obviously, this is about identity, which works well for us. We have no problem with this, right? We know what our identities are. We have some estimate of it. We know very easily like who's likely to be sort of closer to the person we're trying to get to if we think about this search thing. But when we move out to informational objects, there's lots of tagging that's happening. It's not done by experts. This is this has been around for a long time now. This word has come and gone, I think. Folksonomy was this idea of taxonomy coming from the folks, right? Probably never heard of that term. So I think it went like that. Yeah.
Is that relying on like the self-described metadata?
Yeah.
Or would just budget to get more hits?
So this is where lots of people are tagging something and you're not in control of it, right? I mean, you could deploy a bunch of bots and get around, I suppose. But Flickr, the idea was, early on at least, that people would tag it. You'd tag it yourself a little bit, but someone who comes to that photo could add more tags. And that made it more powerful. And it did really help it early on. If you wanted red flowers, put it in there, fantastic. Google was terrible, right? So this may be getting a... But it's this tension between expert curated things and lots of people coming in and adding bits of information. But it makes your network more searchable, because you have identities, you can associate things with each other. Obviously it's true for knowledge in general, right? Wikipedia, you can look at that and see which things are connected to which things, and there are sensible connections. We do have a project, right? We have this project of looking at what happens with the first link on Wikipedia if you click on that. And it does end up at philosophy, which is funny. Actually, it ends up at a little, so this is a simple thing, right? You go to a Wikipedia page, anything, right? Doesn't matter what it is. Click on the first link that's not in the the boxes or whatever, and keep doing that, and you'll end up at philosophy. And you get into a little ring, actually, which has existence, reality, quality, something like that, philosophy, and it goes, right? That's the sync. But it's not, philosophy itself doesn't have a giant in degree. It's only about 600. The United States has the biggest one.
Have you ever played the Wikipedia game? We'll start on the same thing, and you have to try and get to it different things.
Yeah, right. So a student of ours worked on that. Yeah. Yeah. So that fits in with all of this. Yeah. Right. But you can click on anything. Is that right?
Yeah, you can click on anything.
But it has to be in the page. Yeah. So and then you start to understand the structure of it too, because you can kind of, which is a bit like the ladder Adamic thing. You want to get up to a central place, and then you can go down from that. All right. all right, Amazon does this, right? I mean, with the recommender thing, although I think that's all probably, I don't know, maybe it's still good. It did tell me to buy this, of course, very recently. I already own it. Yes, the hoi polloi. This is kind of funny, right? People often use this word to mean the top people. This term, I should say. Hoi polloi is the, right? There's hoi oligoi. That's the rulers, right? The few. Okay. Okay, so here's our nutshell, right? So networks are unsearchable by themselves. You have to have something, you have to know something about how it's formed, which we do, and how it continues to be formed. It's a better kind of social network model. We still, I think there isn't just this beautiful, we've got the Ising model, everyone loves it, and they'll do it over and over. This one is sitting there. Peer-to-peer networks, all sorts of other things, informational search. So I think that's good. Okay, so it's time to go. You can watch this if you want, but I know they won't let me do that anymore. But good. So I'm going to talk about scale-free networks on Thursday, and we'll get through that, and then we'll go into conclusion.
Heart pounding. By design.
Eat more candy. Okay, but that's a small world story. The papers behind that are getting up to 900, 700 citations.
Nå er jeg jævla spent på om jeg har lagt igjen noe mer igjen.
So, these are big things.
Bare grunnrasjon, som det var noe annet som kan spises.
You know what this is? Has anyone seen that?
Tenk
This is a
om jeg
Norwegian
hadde lagt
guy
igjen noe godteri.
who,
Det hadde vært toppers.
the typical Norwegians, right? They're like Amundsen. The English go there to die
Jeg tror ikke det noe.
and write these, sorrowful
alltid lov å
these
håpe.
journal entries. And then Amundsen skis off the other side.
Med
Going, it's
vaselin,
kind of
har
boring.
jeg for så vidt ikke brukt før. Sinksalve.
And you've got
Det
your
la jeg igjen. Det er
Englishman in
ganske mye her,
tweed
altså. Det var
costume.
tydeligvis
So,
bra.
this guy, I don't know, I can't remember the details of what he did, but it was unsupported.
Ja! Ja! Ja!
But he forgot what he'd done. He hid a bunch of food just before he got back for himself to find. And it's like Cheez-Its or whatever. It's just great moment. He's a long way into this. He's gone. He doesn't even remember what he put in there. Or anything, what his name is.
Virkelig? Hæ? La jeg igjen det?
That's also
Det er dobbel pose cheese doodles. Ja! Ja! Jeg er så sulten. Og resten er vel bare søppel. Ja.
I think there's some good.
Ekstra skje. Pumpe til primus, så har jeg hatt 2 stykker allikevel. Ekstra trakt, den har jeg ikke hatt på noe. Ekstra trekktøv.
Alright, you can go. There you go.
Hva er det jeg har tenkt da? Har jeg drevet lagt inn dette her? Jeg har sikkert tenkt jeg har prøvd å spart vekk da. Det er jo ikke mulig. Hæ?
Very good. You can see it on Austin. Lots of things. So good. Yeah. So we need to know what the thing is.
Her er
actually shaped
Mentos. Åh! Her er ost! Hva Jeg har lagt igjen alt her som jeg burde ha lagt igjen på det neste
Hey.
depotet. Ja, ost. Herregud!
This is for you.
Ja, det var det da. Nei,
Understood.
er det
Wow, so the Whoppers are bad.
Jeg blir helt gal!
You may have as many as you want.
Solen jo!
Hey man,
Halleluja!
you've sent a bunch of things that. Okay. Let's see that.
Halleluja! Halleluja! Halleluja!
I also sent you a link to the IPython notebook.